Hello, I'm Charles Jones. I'm a professor in the Department of Geography and Earth Research Institute at the University of California in Santa Barbara. I'd like to thank Professor Michele Reboita for inviting me to give this lecture. And today I'm going to talk about the Madden and Julian oscillation. In this lecture, I'm going to begin with discussing the mean conditions in the tropics, the tropical climatology. And then I'm going to discuss the timescales associated with the MJO and describe how the MJO was discovered. Then I'm going to spend several minutes describing the structure of the MJO. And given that the MJO is an important mode of climate variability, I'm going to discuss, briefly mention some of the implications for this, including teleconnections, interactions with the oceans, subseasonal to seasonal predictions, and climate change. And I'm going to finish with describing how we monitor and predict the MJO, and I'm going to include some references and resources. So what is the MJO? So the MJO, briefly, is a tropical weather pattern that shapes global climate. It is an eastward moving variation in clouds, winds, rainfall, and many other variables near the equator, and it has a time scale between 30 and 60 days. The MJO also interacts strongly with the oceans and can influence variations in mid to polar latitudes. Before examining the MJO in detail, let's review the mean tropical climate, the timescales associated with the MJO, and some statistical methods that were used to discover the MJO. So the satellites orbiting the Earth, they carry instruments that can measure the radiation energy leaving the top of the atmosphere. And this radiation energy is in the long wave part of the electromagnetic spectrum, as we call outgoing long wave radiation. So in regions where we have deep convective clouds, the radiation emitted by the surface is absorbed by the clouds and re-emitted upwards and downwards. The radiation emitted upwards and leaving the top of the atmosphere is going to depend on the temperature of the top of these clouds. And there is a law in radiation called the Stefan-Boltzmann law that says that radiation emitted is proportional to the fourth power of the brightness temperature. And so if we compare schematically a region with deep convective clouds with a region with absence of clouds, or what we know is that in regions of deep convective clouds, the OLR leaving the top of the atmosphere is going to be lower than the OLR leaving the regions with absence of deep convective clouds. Because of this, OLR is frequently used as a proxy for deep tropical convection. In this figure here, it shows the climatology of outgoing long-wave radiation measured by satellites. If we focus in the tropical region, we see these areas with very low values of OLR, and the scale here is in watts per square meter. So we see a region with low values of OLR over Africa, over the Indian Ocean, Indonesia, along the intertropical convergence zone in the Pacific, also along the South Pacific convergence zone, Indonesia. Over South America, we see very low values of OLR over the Amazon basin, also extending over Southeast Brazil. So these regions are where we climatologically observe deep convective clouds on average. Right? And for example, in these areas with high values of OLR, those are regions of suppressed convection. Now, these other plots shows the climatology of the zonal winds at 850 hectopascals. If we focus in the tropical region, we see easterly winds over a good portion of the Atlantic Ocean, South America, and also central to Western Pacific. Over the Indian Ocean, we actually see positive zonal winds, indicating westerlies. So this region of convergence of winds in the lower levels is maintaining the tropical deep convection that I showed in the previous figure. In the upper levels, as shown in this figure, showing the climatology of zonal winds at 200 hectopascals, we actually see easterly anomalies in the upper levels of the atmosphere from the date line 180 degrees east all the way to the African continent here. Over this part of the tropical Pacific, we actually see westerly anomalies and easterly anomalies over the Atlantic and South America. So this is the mean circulation associated with the tropical deep convection, the climatology of OLR. So the MJO is going to be a variation, a departure from these mean climatological conditions. Now, what are the time scales of the MJO? So this plot here, it shows the spectrum of variations in the atmosphere on the spatial scales on the horizontal axis. And in the vertical axis, it shows the temporal variations. So it goes from here on the bottom left, it goes from very small scales and very short-lived variations. These are the regions associated with micro variations and turbulence in the atmosphere. And on the opposite part of the graph, here we see long variations, decadal, centennial time scales, and very long spatial scales, so planetary scales. The MJO occurs in this part of the spectrum, variations between 30 to 60 days. But what is interesting about the MJO, it is that it has a planetary scale. So it's a very large tropical phenomenon. So next we can discuss how was the MJO discovered. And in order to describe that, I'm going to briefly summarize some of the statistical methods that can be used to identify the MJO. In this figure here, it shows the open circles and the thin solid line. It shows some time series. For example, the zonal component of the winds at 850 millibars. So we see lots of variations, short frequency, short period variations, right, in this part of the graph. We can actually visually see that contained with this original signal, there is some slower variation, as indicated by the blue line. Basic statistics that we can use to characterize some of the properties of this time series are the mean and the standard the variance of the time series. So the mean is simply expressed by summing all the data points and dividing by the number of points, and that's the mean. And here is indicated by the horizontal line, right? And the standard deviation given by this formula will describe the departure from the expected value, right? So it gives an idea about the spread of the data relative to the mean value. So those are basic statistics. Now we can use more sophisticated methods in which the variance of the time series can be decomposed in the frequency domain or time scales. And this is accomplished by using a method called the Fourier decomposition. And the result of the Fourier decomposition is usually plotted in a figure that is called the spectral figure, the spectrum of the time series. So schematically, here I'm showing three waves, one with 100 hertz frequency and a given amplitude of A. Then the second wave, it has a higher frequency but a smaller amplitude. And the third wave has an even higher frequency and an intermediate amplitude. And in this graph here, it shows the sum of the three waves. So imagine, as in the previous figure, that we have a time series given by the solid black line here. If we use the Fourier decomposition, we can actually see which waves are contributing to the total variance of this time series. And as I said before, the result of the Fourier analysis is in a plot called the power spectrum. And here is one example. So the horizontal axis is the frequency of the waves, and it goes from 0 to 0.5, but in this case I cropped the figure just to make the figure easy to interpret. So the frequencies go from 0 to 0.25. And the vertical axis is the normalized variance of the time series for each of these frequencies. And the power spectrum is resulting from the Fourier decomposition is given by the thin solid line, as in this case. And there are two additional curves: this smooth solid line here, and the dashed solid line, the dashed line, black line. So this line, the thin smooth line, represents the background spectrum. And the atmosphere, because the atmosphere has memory, so one day is correlated with the previous day, the atmosphere frequently exhibits a red noise background spectrum. That's what this thin solid line indicates. The dashed line is the 95 significance level. So the conclusion from this spectrum is that if we look in this part of the spectrum, frequencies, periods between 30 and 60 days, we see that the time series, the original time series, has a lot of variance in this part of the spectrum, right? And this variance exceeds the 95 confidence level. So here we can say that the time series has a variation that is distinct from the background red noise. So that's the method that Raymond Marden and Paul Julian used in the late 1960s to discover the MJO. So they employed they computed the power spectrum from several time series. And at that time, the data that they used came only from radio sound stations distributed along the tropics. And using this, they were the first to discover the existence of the oscillation. And at that time, in the first paper, they just mentioned, they call this the 40 to 50 day oscillation. And after that paper, they extended the analysis using more radio sound data, and they still call it the 40 to 50 day oscillation. But it was an important discovery. And they, after that, many researchers got excited about this oscillation, and they continue to investigate. And after many years, the oscillation now is simply called MJO, Marden-Julian oscillation, in honor of the two researchers. This figure here is from the second paper, the 1972 paper, and it shows the power spectrum in all the locations that they used in this paper. And it's a little bit hard to see, but they show that the spectrum, the power spectrum, each of these power spectrum has variance in that time on those time scales, 40 to 50 days. And so after that paper, they convincingly showed that the tropical atmosphere has a variation that has these time scales, 30 and 60 days. Also, in this second paper, they employed an additional technique called cross-spectrum analysis. So essentially, you take one time series in one location and the time series in the other location, and you see how they are correlated, but in the frequency domain. And using this technique, they were able to show that the oscillation propagates eastward. Here is two examples of power spectrum. This came from a paper that I did several years ago, and shows the power spectrum using the time series here is brightness temperature at the top of the atmosphere. So I took that one time series of brightness temperature in the Indian Ocean and another one in the Western Pacific. And here I'm just illustrating that that variable has a lot of variance exceeding the red noise background spectrum in the same frequency domain of the MJO between 30 and 60 days. So in the second paper, using more data, they convincingly showed that the atmosphere the tropical atmosphere has this variation of 30 to 60 days. And they actually proposed the structure for this oscillation. So they postulated that in the equatorial region, there is a region of enhanced convection that starts east of Africa and Indian Ocean. So that region of enhanced convection starts to amplify over the Indian Ocean, and it's propagating eastward from the Indian Ocean to the Western Indian Ocean, all the way to the Western Pacific, where it finally decreases. Also, in the zonal direction, they propose that this is part of a cell, so convergence of winds in the lower levels, ascending motion, and once the ascending motion associated with the deep convection reaches the tropopoles, it cannot penetrate the lower stratosphere, the winds have to diverge. And east of the region of enhanced convection, there is actually subsidence, so a region of suppressed convection. So the MJO is frequently seen as this dipole of enhanced convection and suppressed convection. This dipole propagates eastward. Okay, in the next slide, we're going to see an animation of the MJO life cycle in the rainfall cycle. Okay, so the MJO is, as I said before, the MJO is characterized by an eastward propagation of tropical deep convection and rainfall anomalies, propagating from the Indian Ocean to the Western Pacific. And this animation was calculated by Professor Adrian Matthews from the University of East Anglia. And if you want to know more explanation about this, here's the website. So this figure here, the top one, it shows a lag composite of rainfall, total rainfall in millimeters per day, as indicated by this scale. Okay, and you can notice that the rainfall composite coincides with the region of OLR climatology, as I described before, right? So in precipitation over Africa, Indian Ocean, Indonesia, South Pacific convergence zone, intertropical convergence zones, and South America, right? Even using the total precipitation, we can see, if you notice here on the top of the figure is the day. So it starts from negative 24 days before, 15, etc., up to positive lags. Even using the total precipitation, you can see that the enhanced precipitation is actually moving eastward, right? The bottom plot, it shows the same lag composite, but using precipitation anomalies, right? And now we can clearly see that the enhanced precipitation, the blue areas here, they start off the east coast of Africa, get intense, and then propagate eastward. Let me just wait. Yeah, here is the beginning of the cycle, so enhanced precipitation and propagating eastward. And you have the suppressed part of the MJO cycle. So we have this dipole of enhanced precipitation and suppressed precipitation that is propagating along the equatorial region with a time scale of between 30 and 60 days. Now, the MJO has signals in other meteorological variables, for example, in sea level pressure. And this composite here is showing, similar to the previous one, is showing a lag composite of sea level pressure anomalies. So the blue areas indicate negative sea level pressure, and the red indicates positive sea level pressure. And also in the plot, we see this dashed line indicating the thick dotted contour shows areas of enhanced precipitation, and the solid line suppressed convection. So I'll just wait here for the beginning of the cycle, so minus day 0. So here is the enhanced convection, enhanced precipitation that is propagating eastward. And associated with that, we see negative sea level pressure anomalies. And in the region of positive um, uh, suppressed convection, we see positive sea level pressure anomalies. If you pay attention closely, you can see that the response, the plot here is not symmetric relative to west and east, right? So the negative pressure anomalies, they appear to emanate out of the region of enhanced convection, right? So let's wait until day 0 and we can see this more clearly. Yeah, day 0. So you see that it's not symmetric. There is a region of negative sea level pressure anomalies that propagate fast to the east. So this is indication of what is called an equatorial Kelvin wave that propagates eastward. Okay, and also to the west of the region of enhanced precipitation, there are two anomalies straddling the equator. So those are indications of Rossby wave components. See, this, and this anomalies, which will be clear in the next slide. And that's what I meant before. So an equatorial Rossby wave signal is also forced by the MJO rainfall anomalies. Here. So why do this Rossby? If we look at here, if we look at the anomalies, let me just wait until the beginning of the cycle here. We know theoretically that the Rossby waves should propagate westward, right? But if you look at here, they are actually propagating eastward. And why does that happen? And that's because in the subtropics, we have actually westerly winds, so which carry it forces the Rossby waves to propagate eastward. Okay, now let's look at more details about the structure of the MJO. In this plot here, I'm showing a sequence of OLR anomalies that were calculated by using filtered OLR data. So I took time series of outgoing long wave radiation, and I applied a bandpass filter, retaining only variations between 30 and 60 days. And I had a method to identify the MJO, and using the dates only when the MJO was active, I calculate the composite, the average of the OLR anomalies. And this is done by using a lag composite. So it's starting with day 0 here, and it goes every 10 days. The plot here, it shows the red is representative of negative OLR anomalies, and the yellows are positive OLR anomalies. So we see that in the beginning of the MJO life cycle, we start to see negative anomalies developing over equatorial Africa and the Western Indian Ocean. Then 10 days later, the OLR anomalies, the negative OLR anomalies intensify and also extend in the zone of direction. And to the east of the region of enhanced convection, we see actually positive anomalies in the OLR, right, indicating suppressed convection. And 10 days later, the enhanced convection moved even further east, and the positive anomalies of OLR actually decreased. And we see this dipole of enhanced convection and suppressed convection propagating eastward. And we also see signals in South America. So this schematic figure, it summarizes some of these anomalies that we see in this propagation of the MJO. So starting with day 0, here we would have enhanced convection over the Indian Ocean. We have easterly anomalies to the east of the convection, westerly anomalies to the west of the enhanced convection, ascending motion, divergence in the upper levels of the atmosphere. And to the east of the region of enhanced convection, we actually see suppressed convection. And here, because there are no clouds reflecting solar radiation, the winds also are weaker to the east of the convection. Sea surface temperature anomalies are actually positive here. Okay? And this dipole of enhanced convection and suppressed convection propagates eastward. Now, in this case, the enhanced convection is over Indonesia, the suppressed is over the Western Pacific. To the west of the enhanced convection, we actually see stronger westerly winds. And that's because, if you recall, in the climatology over the Indian Ocean, we actually have mean westerlies there. So the winds here are stronger, and they actually cool the ocean because of evaporation. So the sea surface temperature is actually negative to the west of the enhanced convection. And this schematic figure is from the Climate Prediction Center, from the National Centers for Environmental Prediction. And I'll have a link to this discussion further later. Okay, now this other animation shows actually the relationship that I just described before, or in other words, the anomalies in sea surface temperature. This animation was also calculated by Professor Adrian Matthews. So here we are looking at the colored regions show anomalies in sea surface temperature. So blue indicating negative anomalies and reds and orange positive anomalies. And the dashed lines show enhanced rainfall or enhanced tropical convection, so low values of OLR. And the solid lines indicate reduced rainfall or positive anomalies in outgoing long wave radiation. So let me just wait here until we see the beginning of the cycle. So here is the enhanced convection. So we see that to the east of the enhanced convection, enhanced rainfall, we have positive anomalies in sea surface temperature. And to the west, we have negative sea surface temperature anomalies. So it matches the previous schematic figure that I showed this. And this is just another same type of plot. It shows the propagation of enhanced precipitation eastward and the suppressed region of suppressed precipitation. So this dipole propagating eastward. Now, in addition to the eastward propagation of convective anomalies and enhanced precipitation, there is also eastward propagation of circulation anomalies, as in the case of the schematic figure. And this figure here, it shows the upper level divergence, a lag composite of upper level divergence, indicating this part of the schematic figure. So this upper level divergence propagating eastward and upper level convergence propagating eastward as well. Now, I mentioned several times that the MJO is associated with a region of enhanced convection and enhanced precipitation. So how does the atmosphere respond to this MJO convective heating? So the convective heating is an energy source for the atmosphere. So the heating in the atmosphere, due to the large-scale convection and consequent release of latent heat, will force a response associated with Rossby and Kelvin waves. And theoretically, this can be understood, it's summarizing this next slide. So this slide here, it shows a composite. The dates are indicated on top of the figure. And so here schematically, it shows the equatorial, the tropical region from 30 south to 30 north. And this is showing the upper level winds and geopotential height. Okay? And the middle plot, it shows it's a cross section along the equator, and it's showing the U component, the zonal winds, and the vertical winds. And the bottom plot shows the same composite in the lower levels of the troposphere. So the zonal winds and meridional winds and geopotential high. And this is, it comes from a simple model that was originally proposed by Matsuno and Gill in 1980. And it shows the response of the tropical atmosphere to this heating anomaly, right? So if we look at in the upper levels first, right? So the heating is stationary here in the Western Pacific. And we are looking at the response in the upper levels of the atmosphere. If we look at the close to the equator, we see that the winds don't have a meridional component. It is strictly zonal winds, and these winds they actually propagate eastward. So this is the Kelvin wave response that propagates eastward. Away from the equator, on both sides of the equator, we actually see these anticyclonic anomalies in the zone in the circulation. So this is the Rossby wave component. In this case, it has no mean zonal winds, so the Rossby wave actually propagates. It doesn't propagate eastward. Okay, and the same features we can see in the lower levels of the atmosphere. And this figure here is also from the Climate Prediction Center. It schematically shows the structure of the deep convective region and the suppressed here to the east of the region. And so in the lower levels of the atmosphere, we will see anticyclones on both sides of the equator and cyclonic circulation in the lower levels of the atmosphere. In the upper levels, we see anticyclonic circulation on both sides of the equator in the region of deep convective clouds, and cyclonic circulation to the east of the region of deep convection. And divergence, so convergence in the lower levels and divergence in the upper levels. So here is a summary of the three-dimensional structure of the MJO. So when convection is active in the Indian Ocean and in Indonesia, anomalous instabilities exit the area of enhanced convection in the upper levels of the atmosphere and associated with anticyclonic gyres along and behind the area of enhanced convection. So conversely, cyclonic gyres exist behind the areas of suppressed convection in both hemispheres. At low levels, anomalous easterlies and westerlies are evident ahead and behind the area of enhanced convection. The low-level gyres are generally weaker than those at the upper levels. As the dipole propagates toward the Central Pacific, the lower and upper level circulation anomalies become less recognizable and coherent, but remain an important component in redistributing mass around the global tropics. As I mentioned before, so the response of the atmosphere is the response to the heating associated with the MJO will be a Kelvin wave that propagates eastward along the equator, and a Rossby wave that propagates away from the region of enhanced convection. And in this figure here, the background, the figure, it was a figure in a paper from Harry Handel, and it shows when the MJO convection is in the Western Pacific. So here we would see the Kelvin waves propagating eastward and the Rossby wave propagating towards both hemispheres. The one that propagates towards the northern hemisphere will influence weather, especially in the western part of North America. And the Rossby wave component that propagates to the southern hemisphere will actually influence the weather in South America, especially along Argentina and southeast Brazil. So here we see that the MJO is a phenomenon that happens in the tropics. It's a tropical oscillation, can influence the weather globally in both hemispheres. And this other composite, also from Adrian Matthews, shows the stream function in the upper levels of the atmosphere, and in color here. And the dotted line shows the enhanced convection, and the solid line, the suppressed convection. So if we look at the life cycle here, we will see, let's wait just for the beginning of the cycle. So we see the enhanced convection forming of the Indian Ocean and the suppressed, so the dipole moving eastward. We will see the Rossby wave propagation towards both hemispheres. So again, demonstrating the global influence of the MJO. So in summary, the MJO was originally discovered in the early 1970s. The MJO is the most important mode of tropical intraseasonal variations. Intraseasonal because it has these time scales between 30 and 60 days. The MJO propagates eastward along the tropical belt with phase speeds of 5 meters per second, approximately. In the eastern hemisphere, there is a strong interaction between clouds, rain, surface winds, and large-scale circulation. In the western hemisphere, this interaction between convection and large-scale circulation is more moderate. Another aspect that is very interesting about the MJO is that the MJO has a high degree of variability from case to case, and also some interannual variability. The MJO can appear as just one event, so the enhanced convection forming over the Indian Ocean and then propagates eastward. And once the convection reaches the Western Pacific, the MJO just goes quiet for some period of time. Other times, we see one event starting, and once the convection reaches the Western Pacific, another MJO event starts over Africa and Western and Indian Ocean. So the MJO can occur isolated or in many consecutive events, successive events. Adrian Matthew has a very nice paper showing this variability of the MJO. And also the MJO can vary significantly from year to year. Some years we see the MJO very active throughout the entire year. Other years the MJO is very quiet. It doesn't occur. Now, because the MJO is a very important mode of climate variability, it's the most important mode of variations in the tropical region on intraseasonal timescales, it has been found that the MJO has many interactions with other phenomena in the climate system. And Qidong Zhang has two interesting papers that summarize some of these interactions. So the MJO, of course, can influence extreme precipitation occurrences. It has been shown that the MJO can influence the forecast skill and predictability of extreme precipitation, the variability of atmospheric rivers, precipitation in the tropics and exotropics. The MJO appears to interact with the El Nino Southern Oscillation, the Indian Ocean dipole. It has been shown that the MJO influences ocean surface chlorophyll, the thermocline variability. The MJO has the signature of the MJO has been found in the deep ocean. The MJO, because of this Rossby wave propagation towards both hemispheres, it has been shown that it can influence the Antarctic circumpolar current, the length of the day, wildfires, lightning frequency, global electromagnetic field, tornado outbreaks in the US, tropical cyclones, monsoon variability, the North Atlantic oscillation interactions, polar temperatures, and sea ice variability. In the last few years, it has been shown that the MJO interacts with the lower stratosphere and also has some important implications for predictability. So now I'd like to shift towards the last part of this seminar, and just briefly we'll mention how some monitoring and predicting work related to the MJO. So given the important role of the MJO on weather and climate scales, because the MJO occurs on intra-seasonal time scales, so it can influence the weather time scales and also climate variations. Monitoring and predicting the oscillation is a very active research area. Monitoring and predicting the MJO is done by identifying when the oscillation is active. And typically we use outgoing long wave radiations and winds in the lower 850 hectopascals, for example, and upper level levels of the troposphere, also sea level pressure, etc. So the identification of the MJO is usually done by computing empirical orthogonal function analysis of OLR itself, or combined with zonal winds at 850 and 200 hectopascals. So this is called the combined EOF. There are several different ways of doing this. One of them is to apply a filtering so that we retain only variations between 20 and 100 days or 30 and 60 days for these anomalies. And these anomalies, they can be averaged in the equatorial belt or over a tropical domain. And once you do the EOF analysis, we use the first two principal components or time coefficients as an index to identify the MJO. So here are some references that summarize some of these techniques. One was by Matthew Wheeler and Harry Handon, in which they proposed this index that can actually be applied in real time to identify the MJO. And in this case, they use the OLR and zonal winds average along the equator. And this figure here shows the first two EOFs for these variables. In a more recent paper, George Giladiz and co-authors, they revisit some of these different techniques to identify the MJO. And here in this figure, they show the EOFs, but instead of averaging around the equator, they actually computed the EOFs over this domain. And once the EOF analysis is done, as I said, we use the first two principal components to identify the MJO. So usually this is done by plotting the values of the PCs, PC1 and PC2, in this phase diagram. So the horizontal axis is the first PC, and the vertical axis is the second PC. And in this example here, it shows the values of the PCs day by day, right? And the PCs are normalized. So one condition to identify when the MJO is active is that the amplitude is greater or equal than 1. So you take the first normalized PC1 squared, the second PC squared, and you take the square root of that. So when the amplitude is greater than 1, as in this case here, the green dots, the green line, is one condition. But the other condition that is very important to identify the MJO is that the phase of the PCs have to be rotating counterclockwise, which indicates the eastward propagation. And in the PC, the phase diagram is constructed that this rotation, counterclockwise rotation, indicates the eastward propagation from the Indian Ocean towards the Western Pacific and Maritime Continent and Western Pacific. Now, I'd like to show a few resources that are important if you want to learn more about the MJO. And there is here in this slide, there is a link in each of these images. So one site that is very nice, it contains lots of resources, is from the NOAA Physical Sciences Laboratory. And this was put together by George Gladys as well. So here you can download, you can find some references, some publications, MJO indexes, and also you can monitor the current conditions for the MJO. The other site that is very nice is from the NOAA Climate Prediction Center. If you go to the website, there is a link there to the Madden and Julian oscillation. Also, you can see a weekly discussion, not only about the current conditions, but also the forecasting of the MJO. So I encourage you to learn more about this. And the last one is from the UCAR in the US. It has this website called Comet that has some lectures on many different topics in meteorology and also in climate sciences. And if you log in there, you register, and you can search by topics. There are 3 modules that are very nice. One is about tropical climatology, and 2 additional modules about the MJO. So one of them was actually done by Roll Madden. So it's very nice. I encourage you to further read this. And finally, if you go to this site from NOAA, here publication, there are a long list of publications that you can find. Then some additional resources are in this book that my colleague Leila Carvalho and we added. It's a book about the monsoons and climate change, but there's a chapter there about the MJO influence on the monsoons. There is also this recent book, the second edition book. It's called Subseasonal to Seasonal Prediction. We also have a chapter there on the MJO influence on subseasonal predictions. And lastly, another book, Climate Extremes. There is also a chapter on predicting subseasonal precipitation variations associated with the MJO. So with that, I thank you for watching this video. Here's my contact. If you want to get in touch, I'll be glad to correspond with you. So thank you very much.